This paper opens with a striking paradox. A neuron can know exactly what it is supposed to become, and still refuse to grow. Galindo and colleagues, in a 2026 bioRxiv preprint, used that paradox to rethink how we design injectable hydrogels for spinal cord repair. The motivation is the long-standing failure of cell therapy after spinal cord injury. Transplanted cells face a hostile lesion environment, a glial scar, a fluid-filled cavity, poor survival, and poor integration. Injectable scaffolds promise to deliver cells inside a protective tissue-like matrix. But most scaffolds have been judged on whether cells survive, not whether they mature. So the authors engineered a new one, a hyaluronic acid alginate hydrogel cross-linked through hydrazone chemistry. Critically, it needs no calcium to gel, it sets in about a minute, and it can be tuned to roughly 130 pascals, soft enough to match real central nervous system tissue. It also stays stable for 28 days. They then decorated it with cell-adhesive peptides, RGD, which mimics fibronectin, and IKVAV, which mimics laminin. Inside this gel, they ran a 12-day protocol differentiating mouse embryonic stem cells into V2A interneurons, using retinoic acid, permorphamine, and DAPT. The same protocol was run across every condition: unmodified gel, RGD, IKVAV, and a 2D laminin gold standard control. Here is the central result, and it is genuinely surprising. Every formulation correctly switched on the V2A identity genes CHX10, MAPT, SLC17A6. Differentiation was driven by the soluble cues, not the scaffold, but structure was a completely different story. Unmodified and RGD gels gave dense, inert spheroids with no neurites. Only IKVAV produced radial neurite extension of around 200 micrometers, comparable to the 2D control. Same genes, completely different structures. Why IKVAV? The proposed explanation is an integrin language shift. Early neurons express fibronectin-binding integrins, the receptor's RGD targets. As they mature, they switch to laminin-binding integrins. IKVAV mimics laminin, so it speaks the right language at the right moment. RGD is the wrong receptor at the maturation stage. Viability tracked this too. Roughly 75% for IKVAV versus about 50% for RGD. 3 design rules follow. First, differentiation and maturation need to be optimized separately. Second, peptide choice must track the cell's developmental stage. And third, alginate hyaluronic acid is a validated, tunable platform for neural scaffolds. The headline message is this: the scaffold isn't passive packaging, it's half the conversation. The open question the authors leave us with is whether we are underinvesting in scaffold biochemistry relative to cell engineering.